We now consider how to describe the meaning of program graphs, that is, to define their semantics. As a simple example, a program graph might have a memory having just one value, Vx, for the variable x, and one value, Vy, for the value of the variable y. Next, there will be a semantic function that to each action tells how the start memory before the action is transformed into an end memory after the action. For the assignment where y is becoming 1, if the start memory has the values Vx and Vy for x and y, then the end memory still has Vx as a value for x, but 1 as a value for y. For passing, if x is greater than 0, the end memory will be the same as the start memory, only if the condition is satisfied. Otherwise, it will be undefined to indicate that we cannot perform the action. Similarly for passing if x is less than or equal to 0. For the assignment where x becomes x times y, the end memory differs from the start memory in that the value for y is updated. Similarly for the subtraction of 1 from x. Generalizing from the example, a semantic consists of two components. One is a set mem called the memory. Another is a semantic function which to each action describes how a start memory is translated into an end memory. The function may be undefined if the action cannot be performed for the start memory. This is what the hooked arrow indicates. We write that the semantics of the action alpha and the start memory sigma gives the end memory sigma prime. Here, alpha is a Greek letter A and sigma is a Greek letter S. Let us now look at our example factorial program once again. To describe how to execute the semantics on this program, we need the concept of a configuration. This is a pair consisting of a node in the program graph and a memory. As an example, Q2, 3, 1 is a configuration. An execution step then tells us what happens when we follow one edge in the program graph. As an example, from the initial node with memory 3, 7, and doing the assignment y becomes 1, we end up at the node Q1 with x having still value 3, but now y has value 1. Generalizing from the example, a configuration is a pair consisting of a node in the program graph and a memory. An initial configuration is one where the node is the initial node. A final configuration is one where the node is the final node. Whenever there is an edge in the program graph from a start node Q, open circle, to an end node Q, closed circle, we have an execution step. The start memory sigma is transformed into the end memory sigma prime as given by the semantics applied to the action alpha on the edge. Once more, let us take a look at our program graph. An entire execution sequence is then constructed as indicated on the right. We start at an initial configuration where x has value 3 and y has value 7. Following the edge from the initial node to Q1, we obtain the end memory 3, 1. Continuing like this, we take a number of rounds in the program graph and finally arrive at the final node, with x having the value of 0 and y the value of 6. A complete execution sequence is a sequence of steps starting from an initial configuration and ending at a final configuration. Let us take a look at our program graph and let us remind ourselves of the semantics. Now is the time for you to construct a similar execution sequence, but starting from the initial node where x is 4 and y is 4, ending at the final node with some value for x and y that you should determine. Having done this, you should read the section in the book, doing the try-it-outs on the way.